Okay, thank you very much. Thank you, Prof, for inviting me. And can you hear me? Okay, so this is going to work with Erdös-Rényi there. This is part of a big project on neuromathematics supported by CEPID. This paper, the original paper, appeared in GSP last year. And this article is dedicated to Kalikow-decomposition. Okay, so let's start. So I'm really interested in modeling systems of neurons. So it's not a pretext. I really want to do it. Of course, as Anton knows quite well, we must do something very easy in order to be able to have some results. I'm looking for something like the easy model for neural systems. So something which is very simplified, but yet has some of the qualitative features we find in the neural systems. So neurons talk to each other. They file sequences of action potentials. We call the action potential a spike. And each spike has something like 1 millisecond. I'm going to make a discrete time model in which I have a window, time window, and I'll tell for each neuron if it has a spike or not in this small time window. And well, people call this a spike train. Probably I use the spike train during the talk. Let me show you. This is a raster plot. You have several neurons, and you have horizontal axis time. You have neurons here, and I'm indicating the times in which every neuron has a spike. Now, the basic questions are: how is information, external stimuli, encoded in this way? So we believe that the spike trains encode all our perceptions, external world, or feelings, thought. How is this done? I guess people call this neuronal coding, and as a matter of fact, people do not know what is a neuronal code. Whatever I believe that a neuronal code is a product measure. So I'm going to talk to you about a product measure in a space of configurations, time-space configurations. So the second basic question is how to model brain plasticity. So you know the brain is able to create new connections, and it do it all the time. That's how we learn. And that's how we recover from a brain stroke, for instance. And we don't know how to model brain plasticity really. And then you have effects that are well known, like evoke the potentials. You show people pictures of a unknown person. Well, when I'm in Brazil, my joke is say, you show Maradona, nobody recognizes. So here I say, you show Maradona, everybody recognizes. You show my picture, nobody recognizes. You show Pablo's picture, nobody recognizes. Then you show Maradona, and if you have an EEG recording in the person, you will see that there is synchronization. There is a macroscopic activity obtained by synchronizing several thousands of neurons together. And our goal is to find a model in which this kind of phenomena can be obtained in a rigorous way somehow. So this is really what we want to do. Now, we have around 10 to the power 11 neurons. So you could say it's an infinite set of neurons, because 10 to the power 11 is infinite. Where in practical terms, finite is 10, 20, 30. After 1000 is no longer finite. And this is 10 to the power 11. So, a spike train. For each neuron I, we indicate if there is a spike in this neuron at a certain time. Time actually is a time window. So I put here time. Can you read the time here? And then you have spike. You have windows, which are say 3 milliseconds, and you say if the neuron I has a spike, yes or not here. So you have a process which takes value in the set 0,1 to the power I. For experimental data, usually I take window of less 3 milliseconds. Now, there is a background. Models for systems of integrated of neurons exist. Yesterday, Marcelo Magnasco and Neil spoke about the concrete model. So you have a Nobel Prize in the 50s to describe how one neuron evolves. But also you have systems of neurons described by people, several people, including Buenos Aires, Beggs and Plan, and so on. The more familiar model is what they call integrated and firing models. So let me describe it. The membrane potential process of one neuron accumulates stimuli. I'm using stimulus in a very loose way. I want to say difference of potential. It's a more complicated model, and in a few seconds, Pablo will ask me a question. So pay attention, Pablo. Each neuron spikes the probability, which is an increasing function of its accumulated potential. And after spiking, it resets its membrane potential to 0, to minus. So let's put 0. It's not 0, it's something negative, but let's put 0. And restart receiving stimuli. Okay, before that point, Pablo asks me, but this is just a Sampaio model. It's just spare bucks. And, well, it's not, because you don't have mass conservation here. You don't, the spiking neuron does not give to the other neurons something which is proportional to the accumulated membrane potential. It gives some fixed amount which has to do with the synaptic interaction. So it's not a mass conservative model. Now, if you look at this, the picture is, this is a chain. If you look at a single neuron, this is a chain which has a memory of variable lengths. The memory of each neuron goes back to the last spiking time of this neuron. This is in particular the framework considered by Buenos Aires a few years ago, and Eva and I were very much influenced by this paper. But Bruno, for some reason, only considers a finite number of neurons, and this is a serious problem, because we want to speak about the countable set of neurons, countable infinite set of neurons. So our model is the following. So if you only remember one thing of the stalker, this should be the thing we should remember. So I have xt, which is a configuration which tells a time t, a time window t, which are the neurons who have an action potential spike. I is countable, in our case, is countable infinite. And the time evolution is the following. Given the past, every neuron decides what to do in the next step independently of the others. And then maybe Marcelo could make an objection and say, well, what do you do with electric synapse? I not consider electric synapse in which you have some kind of potlatch effect. But this does not seems to change the qualitative features of the model. So formally, I have the probability of time t of neuron I to have activity A of I 1 or 0. I'm considering a finite set of neurons in this infinite set, given the past. So this is the product. And now I must tell you what is the value of the probability for every neuron. So and this is made the most nasty picture. So here you have a function phi of I, and then inside you have several objects. I'll try to explain them to you. So Wj of I, Wj taken to I, is the intensity, the snap weight of the interaction of J to I. It's a real number. It's a real number. Li of t, so you see in the sum here, you count how many spikes you had after the last spike. La of I of t is the last spiking activity. J multiplies xs. So if you don't have J, if you only have Wj, let me write it here. So you have a sum and here you have Wj goes to I, and here you have T S from I L of T time minus 1 xsj. So if you only have this counts how many spikes J sent to I. So you have here J, that is the last spiking time of I before T. So you count how many spikes J has sent to I in this time interval. Now you have another effect, is that maybe there is some kind of leak effect. You lose some of the potential. And this is given by J of the time difference between T minus S. Say for instance, J only take into account spikes which took place in the last don't know how many seconds. Or maybe J decreases this way, okay? Actually, it's more simple with a J which decreases from the mathematical point of view. J simplifies because it gives you a short memory. In reality, J occurs. And then you have this last T minus LA of T, which is kind of an aging effect. Okay?
And the WJI
is a real number.
And fixed.
It's fixed, unfortunately, but we will be obliged in the future to change it. Yes, it's fixed. At the time scale of you are looking at, it's fixed.
So if S is bigger than N prime T and smaller than T minus 1, I understand that excess of J is 0.
Oh, yeah, but while summing, you count how many spikes you received from J. So if there is no leaky effect, if this was 1, for instance, so you just count how many inputs you received from J. Okay, this is the total number of inputs you receive from J.
But T is always bigger than T.
By definition, T is, okay, I'm sorry. You see, Li of T is the supreme of S is smaller than T, such that the neuron I had a spike. It's the last spike in time of I. So that was your question. I'm sorry. I was thinking something else. Thank you, Papa. So now the neurons who had an influence on I are those for which the synaptic weight is not zero. And you have two possibilities. This synaptic weight is positive. This means that the activity of J is excitatory on I. Negative is inhibitory. And in a few seconds, I will tell you some weakness of the paper, which is associated with this. Okay, now let's make some advertising. So this is a new class of models. This is not Markovian. And they have a countable number of interacting components. So it extends in a non-trivial way the class of wonderful models that Spitzer introduced 40 years ago, more or less. 41 years ago, I guess. Because they are not, because Spitzer's model are all Markovian. This is not Markovian. And it also extends the class of stochastic chains with memory of variable lengths introduced by Jean-Marie. And introduced it generally because these models are only locally of variable length. So you have all the interactions, which means that you must be obliged to go back to minus infinity to decide about next step. So this is a chain of infinite order with a non-countable state space. And this is an interesting object from a purely mathematical point of view. Now, Marcelo, I hope that this is also interesting from a biological point of view. And this is a real question. Well, discrete time is not important. Eva and I decided to write it in discrete time because we believe it was more easy for neurobiologists to read in discrete time. Well, that was wrong. It's so difficult for them to read in discrete or in continuous time. So we made a stylistic choice. Our model is reminiscent of the Hawk's process. It's reminiscent. In discrete time, that could be continuous time. It's reminiscent. So, for instance, a wonderful paper by Bremot and Massoulier, but we have a finite number of components, and Hawk's process are usually considered as a finite framework. And we have this particularly interesting structure of having locally this variable length memory. So Hawk's process would be something in which the sum goes back to minus infinity, and here you have a decreasing function to make the sum summable. But this is less interesting from, I guess, the statistical and applied point of view. Okay, mathematical questions. Given the set of interactions, the function phi is an increasing function, something like this. So given phi of I, given the synaptic weights, given the leak effect, does a chain with the above dynamics exist? Is it unique? And the answer, that's the content of our paper, is yes. You have one, I will explain it to you. And then, when we wrote the paper, we said, well, we could invent several models. Now the question is this model able to reproduce qualitative features you find in the literature? So there are a lot of interesting descriptions. So we decided to attack one of the descriptions. The description has to do with the inter-spike intervals. Are they correlated? And then you have a very precise description of data in which consideration about this. And this is both a mathematical and a biological question. And then at the end of the talk, I will show you what we can do about this question. And of course, we have lots of experimental facts to explain. So now I start speaking about the existence and uniqueness. If you have questions, it's time to ask me.
So the support of the function g that you're using, gt minus s, I would say you would get very different qualitative behavior if the support is finite or if it's infinite, or also the speed of decrease.
Yes.
And does this have anything to do with existence and uniqueness, or not at all?
Well, you have two possible types of conditions. I show one of them to you. Actually, in this case, we consider j equal to 1, constant, which is a more, maybe say, difficult case, because if you take j decreasing to it, so you can use the continuity results. Yeah, so I guess j is important because if you want to say things about the way inhibition and excitation place together, you must consider j. But, well, just in the beginning. So in this case, one of the theorems is for j equal 1, constant.
But delta to the t minus s is the most commonly used. Exponential.
Yes, and then you can use the continuity results. But the important mathematical aspect is that we don't need continuity. And this is Roberto Fernandez. This is Roberto Fernandez here. So Roberto uses always continuity. We don't need it.
Antonio, sorry, just G is dependent on J or is equal for all the neurons?
Well, it could be dependent on J, but in our case, I think J in the example we go to 1, yes. But it could be.
Everywhere.
Yes. Actually, the model is not homogeneous, but we still do not have a good anatomic description of the system. I guess this is one of the main questions: how to put extra information in the graph. So let me use some notation. So I call P one given X. So X is the history back to the past. I want to put T since there is a T there appearing. So that's just a notation. It depends. You see, it depends on this. Every neuron I only consider the situation after it last spike time. But maybe J has a last spike time here. And maybe J is influenced by a K, which has a last spike time here. So actually this is an infinite order system. It's not a finite order system. In general, the function, the delivery is not continuous. It's very easy to produce examples, and Roberto is aware. I guess he talked about it in this section. So most of the papers on infinite order chains, as Pablo and Roberto and Servette, use this continuity. Okay, so what kind of hypothesis we use for our theorem? So here we're taking phi constant, and you are supposing it's kind of Lipschitz condition, and here 2 is a clear weakness of the paper. Now I ask you, why is this a weak point of the paper? And exactly. But you know the answer. Yeah. Because you see, we are considering only the absolute values, and this is kind of a Debuschian condition. But the good condition would be a balance between excitation and inhibition. But with our approach, we cannot do it. So that's a weak point, and I hope one of the young, bright probabilists here will be able to get a better result, take into account the fact that the inhibition and excitation should balance each other. So this is a condition which works, but it's not a good condition. Now, we're assuming a spontaneous spike in activity. We don't need, you can formulate the theorem with no spontaneous spike in activity, but with a decrease in J. Spontaneous spiking activity, Marcelo, I guess, plays the role of external stimulus. And so I think it would be interesting if we rewrite the model considering external stimulus. I will come back to this at the end of the talk. So the theorem, under the conditions with delta big enough, we have a unique chain. You have the speed of convergence, and if you have something about J, so the first one is for J equal 1, maybe. You can get it. So these are uniqueness condition. Exists a uniqueness condition. And the proof is based in a perfect simulation construct. So we construct it, and as in many proofs of a perfect simulation, what you do is to make a Kalikow-decomposition. So, what is Kalikow-decomposition? So that's the idea Steve Kalikow had 20 years ago, I guess. It's a way to represent probability transitions of chains of infinite order as a finite combination of transition probabilities of chains of order 0, 1, 2, 3, 4. I learned this in a paper Pablo, Roberto, and Servet wrote a few years ago. And then we used this idea in a more general framework. You remember this paper? With Comex. Ah, not Servet, Comex, yes. Francis Comex, Ferrari, and Fernandez. So what is new here, technically, is to condition on the set of spontaneous spiking activity given by the delta. Remember, you have a delta, which is a probability of having a spike, whatever is your potential. So we use this to make a new decomposition. And so if you use this finite horizontal, which is last time you have a spike, a spontaneous spike in activity, you can do the job, the proposition that you can decompose your transition probability in such a way that for each k you only depend on a finite set of points and on the past until your last spontaneous spike in activity. So this is a conditional decomposition, condition on the realization of the spontaneous spiking, and the reproduction probabilities, the lambda k, are random variables. And then we use this clan of ancestors idea, which also appeared. So this paper somehow a variation on some works by Pablo, Roberto, Nancy on the clan of ancestors. So we use this clan of ancestors idea. Okay, so that's it. Now let's get back to neuroscience. So after writing this paper, we have a perfect simulation procedure where you have, and then you say, well, maybe we should look to the literature to see if you can prove something which appears as qualitative effect. So there is this old paper by Goldberg, response of neurons of the superior auditory complex of the cat to acoustic stimuli of long duration. And they observed that in many experimental setups, the interval between consecutive spike for one neuron seems to be non-correlated. So I'm quoting the famous book by Gessner and Kissler, which says, indicating that the description of spiking as a stationary renewal process is a good approximation. Okay? So that is a basic observation. And it turns out that looking at the data produced by Siddhartha Ribeiro a few years ago, we found the same thing. So I had a set of data produced by Siddhartha Ribeiro from the Brain Institute of Natal, and I had two students, Andrés Rodriguez and Karine Ajnuma. They looked at the data using the smallest maximizer criterion, and they found the renewal process. So I can tell you that you can find this kind of renewal procedure looking at data. But attention, they looked at these neurons in the hippocampus. And maybe 1/3 of the neurons behave this way. 2/3 do not behave this way. So there is something to be understood. Why some neurons behave this way and not the others? Is this due to the particular? They were doing interesting situation. These are hippocampus of hats. They are in a small box, closed small box, in the dark, in a very safe situation. They are free to do whatever they want, a small box. And then they have electrode in the brain. So we got this data. And 1/3 of the neurons of the hippocampus behave, if you look at just a single neuron, as a renewal process. Not a Poisson point process, a renewal process. The inter-spiking activity is not exponential. Now, life is a little bit more complicated than this, because in a more recent paper, now wrote and co-authors, they found evidence it's not true. They found evidence that they are negatively correlated. So if you have a longer spike in time, then it's more likely to have a short spike in activity. So the question is, can our model have this kind of behavior? Can we derive this? These facts are apparently contradictory, but can we account for them somehow? So to do this, we must describe the interacting graph of the system. Until now, we have very general situations like Dobrushin type condition. Now we must say something more specific. And so let me call the neurons vertices. I say that there is a direct edge from neuron J to neuron I to neuron J if the synaptic weight is different from 0. And now the question is, so I have a graph, a direct graph. What kind of structure should this graph, should I give to this graph? And now there is this wonderful paper by Galves and Planck, wonderful because it's well written, lots of interesting ideas. They claim that they have experimental evidence in favor of slightly overcritical Erdös-Rényi random graph. So I will explain what is an Erdös-Rényi random graph. But the Erdös-Rényi random graph is locally is a branching graph. And in the supercritical case, it has just a giant component. So our goal is to be in this giant component. So we will be slightly over the critical point. And I'm quoting here the paper by Galves and Planck. So you see, I put in red, they claim that they found a critical branching process. They claim. So let's do it to see what we get. So that's clear. So I'm telling that I have a neuron. The neuron affects other neurons in a direct way, and then these neurons affect other neurons. And they say that the one they found in their data was culture of neurons and slices of cortex. So maybe neurobiologists say, well, but the culture of neurons is not really like a brain, maybe. But they claim that they have reasons for this. So it's interesting. Okay, so let me tell you what is a critical Erdös-Rényi random graph. So I have a finite set, very big but finite, set of vertices. And then I decided to put an edge between from I to J in an IID way. And to simplify, synaptic weight will be only 1 or 0. Only 1 or 0. but they are choosing an independent way with probability P1 minus P. So that's the classical Erdös-Rényi model, which was invented 61 years in the past, in 53, I guess. Now I take the probability equal lambda over n, and lambda is likely over n. 1 over n is a critical case, so I take it is likely over. So observe that the edges are wij and wj are different and independent. Now, what is the result? So the question. I tell you, I had a spike at time Li of t, and then I ask you, what is the property of having a new spike at time t? So the question is the following. Well, let's suppose Pablo has a blog, a very influential blog. And then one day Pablo writes in his blog, look, this year people should look at direct calculation questions. And then he changed his mind after some time. But Fabio read this blog, so, oh, that's a good idea. And Isacco also, and Fabio also. So then everybody became very interested in direct Erdös-Rényi model. And then this becomes an important motion. At some time later, Pablo reads a blog of written by Roberto, who read the blog by Fabio, read the blog by and then Roberto says, Erdös-Rényi models are interesting models. And Pablo says, well, let's look at Erdös-Rényi models. So an idea which starts with Pablo come back to him. I want to say, is it possible that a spike which took place, you see, I have here I. Then I have a spike here, and I want to know if there will be a new spike here. But maybe sometime sooner, I influenced the J, and J influenced the V, and so on, U, and sometime later, this chain returns. So the question is this possible for this model using the Erdös-Rényi graph? And the result is the following. So that's my question. How long does it take until this influence returns to the starting neuron? And let me call Ci of 1 the sets of the neurons which are directly influenced by I, and then C2, Ci2, C32. So the successive people which are influenced by people are influenced by people influenced by I. So the question, the mathematical question, has to do with how many steps you need until the influence return to I. And the proposition is the following. That's a very easy proposition. The probability of the recurrence time to be smaller than k, it decays this way, where n is the number of neurons and theta is a parameter appearing in the probability of putting a edge. And from this, it follows.
But you don't need a minus
there is a minus, yes. There is a minus. And then this implies the following theorem. So you have a good set of random graphs. This good set of random graphs has a very big probability. And in this good set, for any graph in this good set, the covariance is bound above by 1 minus delta to the power square root of n. And since n is quite big, this is very small. So this tells us that the Goldberg result is somehow reasonable, but it's not independent. I would like to have a lower bound. Okay, so that's the end. I tell you now something about the new steps. I'll be right in time. So next steps. Well, first step is hydrodynamics. There is a first paper on this direction by Eva, Ana De Masi, Enrico Pessuto, and myself. And why is this important? Well, if you want to describe EEG time evolution, if you want to describe functional magnetic resonance imagery time evolution, you need to do some global picture, some kind of local mean field models, mesoscopic models. And in this model, we consider the mean field model. The first step is a very tough paper. Probably you don't have the right tools yet. It's a 42-page paper. But I mean, first step, I hope Pablo and other experts will help us doing next progress on this. So, first thing. Now, yesterday Marcelo showed a very nice situation in which he considered the way external stimulus influence the activity of a single neuron in a leak and fire integrated model. Well, my model is a kind of generalization of this. So we need to put some kind of external stimulus and to prove that different external stimuli drive your system into different states. And state, I mean, in the sense of statistical physics, another law. So this is something which has to be done. Now, we need to include brain plasticity. And this means to include at the same time a time evolution in the graph. The random graph should change as a function of the external stimulus in a different time scale, for sure. Now, where we are trying to do a first step in this direction with Guillermo Cecchina and Eva Locharbach. And finally, the real question is to take experimental data and to say, look, for this data, in this class of model, the model which fits better, in a more economic way, is this one. And this is something which we must develop. There is no no theory now available for this. Statistical model selection is something which must be done. I have students doing on this, work on this, but people like Roberto Imbuzeiro, no, not is Roberto here, should work on this. Hmm?
I raised my hand. No.
Yes, you are. So you should do this, Roberto.
No, I shouldn't have raised my hand.
Okay, so that's the web page of the NeuroMat project. I invite you to visit them, and we have several postdoc fellowships available for bright young probabilists and statisticians. So if you want to work in stochastic modeling in neuroscience, please send me a message. Thank you very much.